So this is chapter 3.3, which is the properties of functions. And the first thing we want to do is discuss even and odd functions. Even and odd functions. So even functions are symmetric with the y-axis. That is, if we were to take the original function and substitute negative x, we would get back the original function. We would get back the same y value. To better see this, let's look at an even function. And if we were to draw a function that's symmetric with the y-axis, that is, if we were to mirror this function on the y-axis, we would have exactly the same picture on the left and on the right. And we have a point here whose coordinates are x and f negative x, or x and y. Yeah? In other words, this x value is right there. The corresponding negative x would give exactly the same y value. Okay, that point would be negative x. So this is f and x, not negative x. Would give me back exactly the same function value, the same y value, if we were to go ahead and make a substitution for negative x. Algebraically, let's suppose we have a function such as f of x equals to negative 3x squared minus x to the fourth power. So the test is that if I were to substitute negative x in here, this is equal to negative 3 times negative x squared minus negative x to the fourth power. And this is just based on the principle that if I were to square negative x, I would have negative x times negative x, which is positive x squared. So this is negative 3x squared minus, and if I were to take negative x to the fourth power, this is negative x times negative x times negative x times negative x, which is positive x to the fourth power. And immediately see that we get back the original function by substituting negative x into this equation. We end up getting back the original function. So typically functions that have even powers only tend to be functions that have even powers only tend to be even functions. Now, odd functions are symmetric with the origin. And what typically happens here is if we made the substitution for negative x, we get back the negative of the original function. And I wanted to just demonstrate how this looks sometimes, and this is just one example. There's could be several scenarios where this happens. So let's take a graph that kind of looks like this. Kind of difficult to draw. And if I have some point on this graph where I have negative x and I have x, this is f, and that y value has changed to negative y. Originally, that f of x, remember the f of x value is the y value, right? And the y value has now become negative y, which is demonstrating that this graph is an odd graph. In other words, if we were to fold it over the y-axis and the x-axis, we would have exactly the same image. Okay. Example of this, and this typically applies to graphs with odd powers. F of x is equal to 5x cubed minus x. So if I made my substitution here for negative x, I would have 5 times negative x cubed minus negative x. And we know that negative x times negative x times negative x is equal to negative x cubed. So this is minus 5 negative x cubed plus x, which is 5x, I'm sorry, this is no minus sign in here, 5 minus 5x cubed plus x, which if we were to take out the negative sign in front of it, we would have 5x cubed minus x. So this is the negative, inside of the parenthesis here is the original function. So this is exactly equal to the negative of the original functions. So this function then is regarded as being symmetric with the origin and odd. Now, a couple more examples. Determine if f of x is equal to 5x to the third power plus 4 is even, odd, or neither. So notice this has one odd power, but then there's a 4 attached to it. So let's do the test. Substitute negative x. This is 5 times negative x cubed plus 4. Which we already know that negative x multiplied by itself 3 times still gives negative x cubed. So this is 5 times negative x cubed plus 4, which is negative 5x cubed plus 4, which is not the original function. So we know it's not even. And then if we were to pluck the negative sign out of it, we have 5x cubed minus 4. And in the parenthesis, we see that we don't have the original function. So this is not the negative of the original function. So it's not odd. So we can say that this function is neither even nor odd. All right, so that is probably going to help you answer some of the questions. I will do more examples from the homework for this in a little bit. Now let's talk about increasing, decreasing, and constant. So I want to draw this picture here. Perhaps let's do a better picture than it. Let's use this one. Yeah, this looks good. And I'm going to put a couple of lines on this, some funny looking lines here. But I want to give you a demonstration of what even, increasing, decreasing, and neither means. Okay, so here I've got my y-axis, my x-axis, and we're going to put this point here at, say, 3, this one at, say, 9, and this one at 10. Okay, all right. Function is increasing if it rises left to right. Function is, and by rising I mean if it's headed up that way. Decreasing if it falls again left to right. So if we're moving from left to right and the function is doing that, in other words, the slope is negative, then we say it's decreasing. Constant if there is no change. Now, we always describe intervals here, even though this might be some point on the graph, let's say 5. If we're describing increasing here, we're going to assume this is 0. It's increasing from 0 to 3. Then between from 0, and you're describing this interval right here from 0 to 3. Then from 3 to 6, the graph is constant. And then from 9 to 10, the graph is decreasing. Notice we're describing intervals on the x-axis. Okay, not points on the graph, but the intervals on the x-axis. That is important when you try to answer these questions. Okay. All right, now I'm going to copy some examples here. All right, so these are some questions from the homework, and we're going to try to answer them. Use the graph below to answer the question. Let's look at what the question is asking. Read the question. Is f increasing on the interval between -5 and 8? And sorry, -8 to -5. So -8 would be between here to here. Okay. -8 to -5. That little piece of the graph, and we can see, yes, that this is increasing. Yes. Okay, between -8 to -5, the graph is increasing on this little part here. That part of the graph is increasing. Okay. Now, you have to look at these graphs very carefully in what they're asking. This is from -2 to +3. And that part of the graph from -2 to +3 changes from decreasing to increasing. Okay? Changes from decreasing to increasing, so it's not increasing on the interval. Okay, next question. It says the intervals on which the graph is increasing. So first notice it's increasing on this part, which is between -9 and +3, -9 and -3. And we want to put these in brackets because there are actual points on the graph, so we have to include the endpoints. Okay, then between right here, it's increasing again, which looks like between -1 and +1 on the x-axis, between -1 and +1. And then it's also increasing between positive 4 and 6. Okay, notice that we need to put this in brackets because there's closed dots along those points. All right, now we have questions where we have to answer about the intercepts. So recall from the previous chapters that we know the intercepts are the points where the graph touch the x-axis and the y-axis. So this is first intercept is at -2 and 0. Then it crosses the y-axis at 0 and 1. Then it touches the x-axis at 2 and 0. The domain, the graph exists between x is equal to -3 to x is equal to +3. Both have closed dots. And the range, the lowest y value is 0, and the highest y value is 1. Right there, that's 1. Part C, increasing. So the graph decreases first. Then it increases, then it decreases, then it increases. So increasing between -2 to 0, and then from 2 to 3. Decreasing between -3 and -2, and between 0 and 2, and not constant. Not constant. And finally, notice that this graph is even because it's symmetric with the y-axis. If we were to fold it on the y-axis, we would get back the same graph. Here we go. Graph is only one intercept on this graph. It's actually marked 0 and 8. The graph has arrows at both ends, so the domain is from -infinity to +infinity. Okay, all real numbers. And the range starts, there's no y values below 0, but the y values continue to increase up to +infinity. So the range goes from 0 to +infinity. Part C, this graph just has one continuous increase over the entire domain, increasing negative to +infinity, decreasing, not, constant, not. And finally, it's neither even or odd because it's not symmetric with the origin or the y-axis, neither. Not symmetric with x-axis or y-axis. So it's neither even nor odd. Intercepts, points where the graph crossed the or touch the x-axis. So the first one is negative pi and 0. Then it crosses at 0 and 0. And then it touches at pi and 0. This is a very restricted domain. The domain is only between negative pi to positive pi. There are closed dots on the end. I need to pause this for a second. Okay, yeah, we were at domain. I see a little problem here. The domain should be restricted because there's closed dots on the end, so the domain is actually bracketed negative pi to pi. In the range, lowest y value is negative 3, highest y value is positive 3. The graph, that's right, increasing, decreasing. Okay, so between negative pi to negative pi over 2, the graph is falling. Brackets because of the dots. Then between pi over 2 and negative pi over 2 and positive pi over 2, the graph does one continuous increase. So increases between negative pi over 2 and positive pi over 2. And then between pi over 2 and pi, the graph falls again. So it decreases between pi over 2 and pi, not constant. And then with regard to symmetry, this graph is symmetric with the origin. In other words, if I were to fold the first quadrant over the y-axis and then fold it on the x-axis, I would get back the same graph. Also notice that pi over 2 and 3 changes to negative pi over 2 and negative 3. In other words, when we change the x value from pi over 2 to negative pi over 2, we get the negative of the y value. Okay, remember this is x and f of x. And the algebraic part of this is if we put negative x, we would get negative f of x. So origin, symmetry. All right, now let's go ahead and further our discussion, and we're going to, okay, so now we're going to talk about minima and maxima. Okay, local minimum or maximum are all the lowest points or the values on the graph, not including endpoints. Okay. Lowest or highest points, and I should say valleys and hills, right? Valleys and hills, or hills on the graph. All right, absolute minimum or maximum includes the endpoints. So let's look at this picture that I drew here, and we're going to try to identify local minimum points and local maximum points, okay? So give me 1 second here. I need to bring over something. Okay, so we're looking at all of the low points on this graph, local minimums. Okay, and we're going to describe a point at, we can't include this endpoint, so -3 and 2. Right here we have 0 and 2.5, and we've got another one here, 7 and -4. Make sure that this part of the graph is a little tricky, yeah? That part doesn't look like a minimum point, but let's draw it back. So it goes that way, yeah? Okay. All right, so local minimum at -3 and -2. 0 and -2.5. And 7 and -4. Sometimes this could be written as f -2 is equal to -3, f -2.5 is equal to, sorry, I have this backwards. F substituted with -3 equals to 2. F substituted with 0 is equal to -2.5. And F substituted with 7 is equal to -4. So these are just two different formats for the answer, okay? Then the local maximum -6 and 2, -2 and 1. I'm going to mark those with this, and 5 and 4. Okay, now includes the endpoint, and the absolute value is, absolute minimum is the highest or lowest point, and including the endpoint. I forgot to mention that, okay? So absolute maximum is the single point that's the highest on the graph, including the endpoint. Now, this end of the graph goes up to infinity, and we can't call that the absolute maximum because we don't know where infinity ends, right? But the absolute highest point on this graph, this is an absolute maximum, is located at -8 and I'm sorry, at 5 and 4. 5 and 4. In other words, when x is equal to 5, the y value is 4. And the absolute minimum, by the way, notice that the absolute max and the local max could be, and one of the local max could be the same. Okay, then the absolute minimum point of the graph is this point right here, absolute min, at -8 and -5. In other words, when x is equal to -8, y is equal to -5. There's different ways of stating your answer. Okay, so remember, we don't include an open end. This is not an endpoint because this point is going up to infinity. Yeah, so it's not an endpoint on the graph. Okay, I want to copy a few of the homework problems, so I'm going to pause this for a second and do that. All right, so here are examples from the homework of finding minimum and maximums. Let's use the graph to answer the question. List the values at which there's a local minimum, the x values. So in this case, local minimums occur at x is equal to -3 and x is equal to +1. Those are the values in the graph. And then what are these local minima? So these local minima, you have to give the x value. Let me just take a second here to make sure about that. Okay, yeah. So both of these minimum occur at y is equal to -1. Both of them occur at the y values, and these are the x values. In other words, the minimum occurs at -3 and -1, and then 1 and -1. In each case, the y value is the same, as you can tell from the graph. Find the absolute minimum on -10 to 7. So consider -10 to 7, which is the entire domain of this graph. The absolute lowest point occurs right there when x is equal to -8. The y value seems to be -4. Okay, local maximum and local minimum for this graph. So again, I need to check the format for the answer before I answer this for you. Okay, so it's asking the numbers at which the local maximum occur, which is at -2, -π/2, and -5. In other words, when f x is equal to negative pi over 2 and f of x is equal to negative 5. And then the local maximum occurs at pi over 2 and 5. In other words, when x is equal to positive pi over 2 and f of x is equal to positive 5. One final example. For the graph of f of x shown to the right, find the absolute minimum and absolute maximum. So absolute minimum includes the endpoints. Absolute maximum occurs at 3 and 6 when x is equal to 3, y is equal to 6. Absolute minimum occurs at 7 and 1 when x is equal to 7, y is equal to 1. Local minimum occurs at 4 and 2 when x is equal to 4, y is equal to 2. And local maximum occurs at 5 and 3 when x is equal to 5, y is equal to 3. All right, the final thing I want to discuss with you is something called the average rate of change. Average rate of change, known as the AROC. There's a formula for this. Average rate of change equals to FB minus FA over B minus A. Okay? So here's an example of how to use that. For f of x equals to 2x squared plus 4, find the average rate of change A from 1 to 3, B from negative 2 to 0, and C from negative 1 to 2. So always identify the first value as A, the second value is B for each case, okay? A and B. So average rate of change is FB minus FA over B minus A, which is F substituted with 3 minus F substituted with 1 divided by 3 over minus 1. So F substituted with 3 is 2 times 3 squared plus 4. That's 3 3s, 9 9 2s, 18, and 4 22. And F1 is 2 times 1 squared plus 4, which is equal to 6. So substituting in my formula, I have 22 minus 6 over 2, which is equal to 8. Average rate of change here is F0 minus F negative 2 over 0 minus negative 0 B minus negative 2. Okay, so let's do a substitution. Substituting 0, F0, we have 2 times 0 squared plus 4, which is equal to 4. So this is 4 minus negative 2 substituted give 2 times negative 2 squared plus 4, which 2 2 is 4, 4 2 is 8, plus 4 is 12. So this 4 minus 12 over 2. Which is equal to negative 4. And finally, average rate of change, F2 minus F negative 1 over 2 minus negative 1. So we know, we need to figure out the values. F2 is 2 times 2 squared plus 4, which 2 2 is 4, 4 2 is 8, plus 4 is 12. And F negative 1 is 2 times negative 1 squared plus 4, which is 6. So this is 12 minus 6 over 3, which is equal to 2.